In this video, we're going to learn how to find the horizontal asymptotes of rational functions. Remember that asymptotes are lines that our functions go towards as we trace their graphs. Unlike polynomials, rational functions do not necessarily have to go up to infinity or down to negative infinity when we trace their graphs to the right and to the left. A rational function has a horizontal asymptote if the outputs or y-values go towards a finite number as we trace to the right and to the left. So if we want to find the horizontal asymptote for a rational function, essentially what we need to do is determine its end behavior. Let's go through an example. In example A here, we want to find the horizontal asymptote of the function f of x equals 2x cubed plus 3x squared minus 4x plus 5, all divided by x cubed minus x plus 1. So what we want to ask ourselves is what happens to our function or the outputs of our function as we trace our graph to the right and as we trace our graph to the left. And what that means is what happens as we plug in larger and larger values in for x, either positive or negative. The way our rational function is written right now, it's a little bit difficult to answer that question. So instead, we're going to rewrite it in a slightly different way. What we're going to do is we're going to factor out the highest power of x from both the numerator and denominator. So in the numerator, if we factor out an x cubed, what would we be left with? To figure out what's left, we just divide each term by x cubed. So first, 2x cubed divided by x cubed just leaves me with 2. 3x squared divided by x cubed leaves me with 3 over x. Negative 4x divided by x cubed gives me negative 4 over x squared. And then lastly, 5 divided by x cubed gives me 5 over x cubed. We can always check if we factored things correctly by taking the x cubed and distributing it back to each of our terms inside. We should end up with the original polynomial that we started with. Now let's repeat this process with the denominator. So in the denominator, if we factor out x cubed, what are we left with? So take each term here, divide each by x cubed, and see what we get. Our first term, x cubed, if I divide this by x cubed, we're just left with 1. Next, if I have negative x and I divide by x cubed, I'm left with negative 1 over x squared. And then lastly, 1 divided by x cubed is just 1 over x cubed. Now, our goal is to figure out what's happening to my function as we plug in larger and larger values in for x. So we won't be plugging in numbers like x equals 0. For that reason, we can cancel out these x cubes from both the top and the bottom. So our function would look like 2 plus 3 over x minus 4 over x squared plus 5 over x cubed divided by 1 minus 1 over x squared plus 1 over x cubed. So again, let's ask ourselves what happens as we plug in larger and larger values in for x. Specifically, let's think about what happens to these fractions that we have here. When we plug in larger and larger values of x, the denominators in those fractions would get larger and larger, which means the size of those individual fractions becomes smaller and smaller. They get closer and closer to 0. So as x goes to positive infinity or negative infinity, these fractions each get closer and closer to 0. So what's left? Well, all that's left is the 2 in the numerator and the 1 in the denominator. So we can say that as x goes to infinity or x goes to negative infinity, our function f of x, the outputs here, gets closer and closer to 2 over 1, which is just 2. So here, in terms of our graph, this means that as we trace our graph to the right, our outputs or our y values are getting closer and closer to 2. And also, as we trace to the left, our outputs or our y values are getting closer and closer to 2. Since our outputs are going closer and closer to 2 in either direction, we would say that our horizontal asymptote is y equals 2. So again, I'm going to write here our horizontal asymptote, which I'll abbreviate with HA, is y equals 2. Let's confirm this by looking at a graph. Typing in our function, we have 2x cubed and then plus 3x squared minus 4x plus 5. All of this divided by x cubed minus x plus 1. We see here that our graph will go towards a finite number as we trace to the right and as we trace to the left. And let's type in our horizontal asymptote, y equals 2. And again, we see that when we trace our graph to the left, our graph gets closer and closer to the horizontal line y equals 2. And when we trace our graph to the right, our graph gets closer and closer to that horizontal line y equals 2. This is because the outputs or the y values of our function gets closer and closer to 2 as x goes to infinity and x goes to negative infinity. Now, one thing you might notice is that our outputs went towards 2 divided by 1. The 2 is the leading coefficient of our numerator, and even though there's not a 1 explicitly written here, we can write a 1 times x cubed there. We see that the 1 is the leading coefficient of the denominator. This is because when we factored out the x cubes, all that's left are those leading coefficients with a bunch of fractions afterwards. And when we plug in large values in for x, all of these fractions will get closer and closer to 0. So all that's left are those leading coefficients. And it turns out this pattern will hold true as long as the numerator and denominator have the same degree. So in general, if the degree of the numerator is equal to the degree of the denominator, then our horizontal asymptote is always going to be y equals the fraction of the leading coefficients. Knowing this pattern will help save us some time. Let's use this in our next example. In example B, we want to find the horizontal asymptote of the function g of x equals negative 5x squared plus 3x plus 1, all divided by 2x squared plus 4x minus 5. In our example here, the numerator and denominator have the same degree. They're both degree 2 polynomials. And so, according to our pattern, the horizontal asymptote is going to be a fraction of the leading coefficient. The leading coefficient in the numerator is negative 5. The leading coefficient in the denominator is 2. So our horizontal asymptote is going to be y equals negative 5 over 2. Because of our pattern, we didn't need to do any work at all. But remember that the reason behind our pattern is we can always factor out an x squared from both the numerator and denominator. If we do that, we'll be left with a negative 5 plus some fractional terms, and then in the denominator, we'll be left with 2 plus some fractional terms. And so, as x goes to infinity or as x goes to negative infinity, all of those fractional components will go to 0, leaving us with negative 5 in the numerator and 2 in the denominator. That's why as x gets larger and larger, our outputs or our y values will go towards negative 5 halves. Let's confirm this on our graph. Let's first disable our previous graphs. Now let's type in negative 5 x squared plus 3x plus 1, all divided by 2x squared plus 4x minus 5. So we have this graph here. Our horizontal asymptote, we found that to be y equals negative 5 over 2. And we see here that if we were to trace our graph to the left, it gets closer and closer to that red line. If we trace our graph to the right, it gets closer and closer to that red line. So again, as long as the degree of the numerator is the same as the degree of the denominator, our horizontal asymptote is going to be y equals the fraction of the leading coefficients. So you might wonder, what if the degrees are not the same? In example C here, we want to find the horizontal asymptote of the function f of x equals 2x squared plus 5x plus 1, all divided by 3x cubed minus 7x minus 2. This time, the degree of the numerator is 2, the degree of the denominator is 3. If we want to find the horizontal asymptote, we would need to determine the end behavior for this rational function, which means we want to ask ourselves, what happens to our function or our outputs as x goes to infinity or as x goes to negative infinity? Just like before, it's a little bit difficult to answer this question when our function is written in this way. So what we're going to do is rewrite it in a slightly different way. We're going to do some factoring. We're going to factor out the highest power of x from all of the terms in the denominator and from all of the terms in the numerator. So the highest power of x in the denominator is x cubed, so we'll factor that from both the numerator and denominator. Let's start with the denominator. If we factor out an x cubed, what's left? So take each term here and divide it by x cubed. If I have 3x cubed divided by x cubed, we're just left with 3. If we have negative 7x divided by x cubed, we're left with negative 7 over x squared. And then lastly, if I have negative 2, divide that by x cubed, we have negative 2 over x cubed. Now in the numerator, we're also going to factor out x cubed. So what's left? If we have 2x squared and I divide by x cubed, we're going to be left with 2 over x. If we have 5x divided by x cubed, we're going to be left with plus 5 over x squared. And then lastly, 1 divided by x cubed gives me 1 over x cubed. Since we're interested in the end behavior, we're going to be plugging in x values that get larger and larger. And so we're not going to be plugging in x equals 0, which means I can cancel out these x cubes from both the top and the bottom. So our rational function looks like 2 over x plus 5 over x squared plus 1 over x cubed, all divided by 3 minus 7 over x squared minus 2 over x cubed. Now we're ready to ask ourselves, what happens to the function or the outputs here as x goes to infinity or as x goes to negative infinity? Meaning what happens when we plug in larger and larger positive values in for x and larger and larger negative values in for x. Specifically, let's think about what happens to these fractions here. As we plug in larger and larger positive or negative values in for x, the denominators of those fractions are going to get larger and larger, which means the overall size of those fractions gets smaller and smaller. So eventually, these fractions here will all get closer and closer to 0. And so what's left? In the numerator, all of those terms here gets closer and closer to 0. In the denominator, what's left is the 3. So we see here that as x goes to infinity or as x goes to negative infinity, our function goes towards 0 in the numerator and 3 in the denominator. And 0 over 3, that's just 0. So what we're saying here is that as we trace our graph to the right or as we trace our graph to the left, the outputs or the y values of our function gets closer and closer to 0. That's why our horizontal asymptote is going to be y equals 0. Let's take a look at the graph to confirm this. Our function is 2x squared plus 5x plus 1, and we're dividing by 3x cubed minus 7x minus 2. And we see here that as we trace our graph to the right and as we trace our graph to the left, it seems like my graph is getting closer and closer to the x-axis. So our horizontal asymptote here is y equals 0. Again, as we trace our graph to the right and as we trace our graph to the left, our graph gets closer and closer to that red line. So what seems to be the pattern here? Well, if the denominator has a higher degree than the numerator, when we factor out the highest power of x from the denominator, the numerator will be left with just fractions, and the denominator will be left with the leading coefficient and then a bunch of fractions. And so as x gets larger and larger, the numerator will all go to 0, and then the denominator, what's left, will be the leading coefficient. And so your output will go to 0 on top and something that's not 0 in the denominator. And 0 divided by something that's not 0 is equal to 0. That's why in these situations, the horizontal asymptote is going to be the x-axis or the line y equals 0. So in general, our pattern is if the degree of the denominator is larger than the degree of the numerator, the horizontal asymptote is the line y equals 0. Now that we know this pattern, we can identify horizontal asymptotes really easily. In example D here, we want to find the horizontal asymptote of x cubed minus x squared divided by x to the fifth plus 2x minus 3. Here, finding the horizontal asymptote is really easy. The denominator is a degree 5 polynomial. The numerator is a degree 3 polynomial. Since the denominator has a larger degree than the numerator, we know right away that the horizontal asymptote is the line y equals 0. Let's confirm this on our graph. Let's disable our first graph. Now let's type in our new rational function, x cubed minus x squared. All of this divided by x to the fifth power plus 2x minus 3. We see that as we trace our graph to the left and as we trace our graph to the right, our graph gets closer and closer to the x-axis, so our horizontal asymptote is y equals 0. So we've seen what happens when the degrees are the same. We've seen what happens when the denominator has a larger degree. Now what if the numerator has a larger degree? Well, it turns out that when the numerator has a higher degree, we no longer have horizontal asymptotes. Instead, we'll sometimes have something called an oblique asymptote, and that's what we'll look at in our next video. So in this video, we learned how to find the horizontal asymptotes of rational functions. We saw that if the degree of the numerator and the degree of the denominator were the same, the horizontal asymptote is y equals the fraction of the leading coefficients. If the degree of the denominator is larger than the degree of the numerator, then we know that the horizontal asymptote is y equals 0.